So today I thought we'd go over the practice final exam in its entirety. Just run through all of the questions. And if you have any questions along the way as to why or what or how, don't hesitate to ask. Tonight is the night to do a review and get you guys comfortable with the final exam. Okay, so in the on the final exam will be 50 questions. It will be entirely multiple choice. Okay. $50 questions for our bonus. Okay, all multiple choice. So that's why if you look on the grade book, it'll say like final exam scored out of 46 or something. So that just means if you get all 50 questions correct, you know, all 50 correct would be, you know, 50 divided by 46, you'd get 108.7%, okay? So there's a fairly generous amount of extra credit built into the final exam, and so, you know, on your handout that's already factored in, and so it might say you need, you know, 105% if you want an A+ or something like that, and that will correspond. You know, it'll say you need, you know, 48 questions correct or something like that, okay, or 49 questions, something like that, okay. All right, and so and again, 80% will be about chapters 7 through 9, and then approximately 20% chapters 1 through 6. And the chapters 1 through 6, these will be no calculations, all conceptual. All conceptual or definition. All right. And that will be it for the course. I hope you've liked it. If you liked the class, you know, I appreciate your evaluations, of course, and for you guys being here. You can also consider leaving a review at ratemyprofessors.com or a site like that. Okay. I know there's a lot of reviews there already, but it's always good to have recent reviews. Okay, so. You know, whenever students look up professors and things like that, you know, if they see a well-rated professor, they're more likely to take that course, and so, you know, I appreciate that, okay? And I think UCLA Extension has kept me around because I've generally gotten pretty good reviews, so. And it does make a difference. If someone gets poor reviews, they're not asked to return. So, so I'm always a little nervous, but, okay. Anyway, let's we'll get started here. So we'll take a look at this first question. It says, a study is performed to understand the relationship between bright lights and headaches. And it says some people were exposed to bright lights and other people were exposed to less bright lights, and some experience headaches and others and both groups, people complain about headaches. All right. So so let's see what happens here, right? Okay, so we're looking at the conditions, and we've got the independent and random condition. Independent and random. Okay, and when we look at this, it says we have two samples, right? We've got those that were exposed to bright lights and those that were exposed to less bright lights, okay? So we have two samples, but both of them were randomly selected, okay? Two samples, both randomly selected. So this condition is met. All right. And then the next condition that we have listed is the big population. I know this is maybe it's a little bit out of order from what we're used to. The big population condition. So here the population would be everyone who could be exposed to lights. Okay. So the population is everyone who could be exposed to lights. So that's going to be a very big number. So in the millions or billions, okay? So the population is definitely big enough, okay? Okay. And then lastly, we have the large sample condition. Okay, and so here we need at least 10 successes and 10 failures. And we have two samples, so at least 10 successes and at least 10 failures in both samples. Okay, so if we look at sample 1, or at least the first sample listed, we had 20 who had headaches, so that arbitrarily we can label a success, or I'll just say 20 say yes. And because we have 80 total, that means 60 say no. Okay, and we look at sample 2, and we have 12 yeses and a total of 90 people, so that means we're going to have 78 no's. Okay. Okay, and all of these numbers are all greater than 10, so this condition is also met. All numbers are greater than 10, or greater than or equal to 10, so condition is met. Okay, so as far as this problem goes, no conditions are violated. So far, so good? Okay. So going on to the next problem. I think I can get all of these. So in problem 2, we'll take a look. Okay. So we have a independent and random condition, and it says we have randomly selected subjects. Okay, so this condition is met, and then we'll look at the big population. Okay, so here we're looking at how common a disease is. So the population is everyone in the world. Okay, or at least the country of that we're interested in. So everyone in the world, because if we want to find out the overall prevalence of a disease, we want to know kind of the prevalence, you know, across the world or something like that. Okay, so the population would be everyone in the world. This condition is met. Okay, let's look at the large sample condition. And we need at least 10 successes, so it says 2% of them have the disease. So we do, you know, n times p. We have 300 times 0.02, and here we only get 6, okay? So n times p is 6. This is not greater than 10. Greater than or equal to 10. So we don't have enough successes, not enough yeses, okay? As for, you know, we could check n times 1 minus p, and we would get 300 times 0.98, and we would get 294. This is greater than or equal to 10, but this is not, okay? So this condition is not met. So for number 2, it violates the large sample condition. Okay. And what this means is that, you know, if any of the conditions are violated, you would not be able to perform statistical inference. You'd have to do a, you know, more complicated method, okay? Because all of the methods we've learned in this class depend on the central limit theorem. Okay, so if you come across something like this, you would not be able to use the normal model or central limit theorem for the analysis. Yeah.
But these can technically be solved with other forms of statistics in a more advanced form.
Yes, yes. We can answer questions with you know, more complicated methods. That is true. Okay. Okay. Number 3, it says a student has to conduct a survey for a school project. He goes around the school campus and interviews people he meets. He finds data from 100 people and finds that 45 of them answered yes. Are any conditions violated? Okay, this is not a random sample. Okay. So this is so the independent random condition is violated. The sample is large enough. We don't know anything about the population. Population size is not given, so I guess it's ambiguous there. As far as the questions on the final exam go, I've made it very clear. There's not going to be any ambiguity about whether a condition is met or not. Yeah.
So I remember when we took the quiz with this, there was a 5th section that said 2 or more have been violated.
Right.
Would it be like that or just like this?
So. As far as the final goes, there will be no ambiguity as far as, you know, if 2 conditions are violated, it'll be clear that 2 conditions are violated. In this one, there's some ambiguity as to whether the big population condition is met or not, because I don't have any information about the population size in the problem. Okay. On the final exam, I've made sure that there's no ambiguity in these questions.
But that will be an option on the final.
You know, I don't recall off the top of my head, but could be. All right. And it says a company, here it says a company wants to survey its employees. It has 800 employees and decides to select 100 of them. And so here again, there's some ambiguity as to whether the sample is large enough. But right off the bat, we can see that the population is not big enough, right? So the big population is violated. Okay, so population is equal to 800 people, 800 employees. Our sample is 100. 100 times 10 is 1,000, which is more than our population. Okay. We good here? Okay, so let's take a look at questions 5 through 10. Here we'll Okay, it says a farm wants to test 2 different diets for their cows to see which diet causes more weight gain. They randomly select 10 cows to give diet 1, and they select 12 cows for diet 2. After 2 weeks on diet 1, so it goes on and it lists off how much the cows, how much weight they gained, and their standard deviation, and things of that. Okay, and it says the following questions refer to a 95% confidence interval for the difference in average weight gain. Okay. So it's very clear that we're dealing with confidence intervals, okay? And are we dealing with means or proportions, and do we have 1 sample or 2 samples? Okay, we're dealing with means, and we have 2 samples, right? Okay, so as far as formulas go, we can use this thing. Confidence intervals means 2 samples. You don't have to use this formula page, but I created it with the intent of it being helpful, but so you are allowed to. So for the final, you're allowed 1 sheet of paper, writing on the front and back. If you want to use this formula sheet as one side and fill out the back side with other things, or and there's still there's space here also. That's up to you. You do whatever you want. And if you want to rewrite these yourself, that's fine as well. Okay, so this is what we need. Okay, so 95% confidence interval. What will be the center? The center is always the part before the plus or minus. Okay, so that's going to be x bar 1 minus x bar 2. In this case, that's going to be, so as far as number 5 goes, it's going to be 15.2 minus 12.6, which is going to give us a difference of 2.6. So that will be the center of our interval. Okay. The confidence interval, what will we use for T star? Okay, so T star will be a 95% confidence. And we're going to need to figure out the degrees of freedom, okay? So the degrees of freedom will be n minus 1. We've got 10 and we have 12, okay? So degrees of freedom is equal to n minus 1. So we're going to use 10, that's the smaller between 10 and 12. So 10 minus 1, we have 9 degrees of freedom. And at 95% confidence, 2.262, I believe. Is that what we're getting? And then, so continuing on, the standard error, we're going to just plug in the values that we have. So a lot of times it's useful to label all of your values. Okay, so x bar 1, 15.2. Let me space these out a little bit. Okay, x bar 1 is 15.2, and the standard deviation S1 is 4.1, and N1 is 10. X bar 2 would be 12.6. S2 would be 3.4, and N2 would be 12. Okay, so as far as the standard error goes, we would just plug in these values. I got 4.1 squared over 10 plus 3.4 squared over 12. Okay, so let's try this out. 4.1 squared over 10 plus 3.4 squared over 12. Okay, and I get 1.626. Okay, and so as far as the interval itself goes, I've got 2.6 plus or minus 2.262 times 1.626. It's coincidentally a lot of 2's and 6's in this, huh? And so let's see what this comes out to be. 2.6 plus 2.262 times 1.626. And I get 6.278 on the high end. And on the low end, I just change that plus to a minus, and I get negative 1.078. So okay. Number 9 says, do we conclude that there's a difference in the average weight gain? How would we decide if there's a difference in the average weight gain or not? Yeah, is it all positive or all negative? It's not, right? So 0 is in the interval. Okay, so at 95% confidence, we do not have evidence that there's a difference in average weight gain. Is that okay? Yes.
So where does this 0 from?
The zero means, no, the 0 comes from whenever you're comparing two samples, the means of two things. Basically, we want to know, so no difference would mean that the difference is equal to 0, okay? And we want to know, is it possible that there's no difference? Or is it plausible for there to be no difference? And that means if 0 is inside the interval, it is plausible that the difference is 0, okay? If 0 is inside the interval, that means it's plausible that the difference is nothing or the difference is 0. And so if we ask, do we have evidence that there is a difference, that means we don't want to see 0 in the interval, okay? But because we do, we say we don't have evidence that there's a difference, okay? Number 10, if we decided to make a 90% confidence interval instead of a 95% confidence interval, what would happen? Okay, our interval would become more narrow. Okay, the only value that would change would be the t star. T star would become something smaller. I'll say become smaller. So that means the interval will be narrower. Find T table and Z table. Okay. We good there? Great. All right. try this here. All right, it says, at the ruler and yardstick factory, a machine is suspected to be defective. The yardsticks it produces are supposed to be 3 feet long. And you measure a random sample of 40 yardsticks and find that the average length is 3.02 feet with a standard deviation of 0.03. Is this evidence that the machine is producing yardsticks that are too long? Okay. So the key here is that it's asking if the yardsticks are too long, and so in that case, it's asking, is this a one-sided test or a two-sided test? Okay. So right off the bat, we know we're dealing with a hypothesis test, right? Okay. And then here, you know, question 12, it just says hypothesis test straight up. So we know we've got a hypothesis test. And do we have means or proportions, and do we have one sample or two? Yeah, we got means and it's one sample. All right, so that's going to shape how we do everything. So I'm going to go ahead and just copy this little segment right here. So this is our reference right here. We got hypothesis test, means one sample. All right. So is it one-sided or two-sided test? Okay. So because it's asking if it's too long, we know our alternative will be in the form of mu is greater than something. And so, you know, some value here. So this is going to be a one-sided test. Okay. All right. Number 12 says, what would our hypotheses be? Okay. So we've got the null hypothesis, and we have an alternative hypothesis. The null is that mu is equal to some number. What number should we put in? 3 or 3.02? 3, right? We want to see if the yardsticks themselves are 3 feet long. And then the alternative, we want to know, are they too long? So is it greater than 3? That will be our set of hypotheses there. So for number 13, we got to find our test statistics. So first we're going to start off with finding out our standard error, and then we're going to go and calculate our test statistics. So let's just go through. We've got x bar. This is equal to 3.02. Our standard deviation is 0.03, and our n is 40. So our standard deviation is s over the square root of n. I have 0.03 divided by the square root of 40. Okay, and I get, for this, I get something along the lines of 0.0047434. Here, I'll show you. So I got 0.03 divided by the square root of 40. Okay, so 0.0047434. And then that's my standard error. So my test statistic t is x bar minus mu 0 divided by the standard error. Okay, so I have 3.02 minus 3 divided by 0.0047434. Plug in the answer, and I get 4.216. So this is my test statistic, number 13. So now I want to find my p-value, okay? So because I have, the alternative has a greater than sign, that means my p-value is equal to the right tail area. Okay. I have 39 degrees of freedom, right? Degrees of freedom is 40 minus 1, 39 degrees of freedom. We're going to round down and use 30 degrees of freedom. Okay, and we're going to go to the t-table. At 30 degrees of freedom, we're going to look for the value, the test statistic 4.216. 4.216 is greater than the last number there, 3.396. The last column in degrees of freedom equal to 30. Okay, so that means our right tail area and thus our p-value is less than the column heading, which is 0.001. Okay. Did I make a mistake?
Yeah, you used the DF29.
I used 29?
Yeah.
Oh, I apologize. Oh, yes. 3.385. Okay. Thanks. Okay. Well, my answer remains the same, but... so there we go. Okay, so 4.216 is greater than 3.385, which is the last column in degrees of freedom equal to 30. And so that means our p-value is less than that column heading, which is 0.001. Okay, so the p-value here would be p-value is less than 0.001. Okay, so if number 15 says if alpha is 0.05, what is our conclusion? Okay, our p-value is less than alpha. So that means we reject the null hypothesis. Okay, and we would say we have evidence that the machine is producing yardsticks that are too long. Okay. And then number 16, if the conclusion that we just made, so our conclusion was that we rejected the null hypothesis, what kind of mistake did you make? Yeah, so if our decision to reject the null was wrong, that is a type 1 error. Still good? Great. All right, here it says researchers believe that 14% of the population is left-handed. A local school decides to see if their students have a different proportion of left-handed people. The school has a total of 1,500 students, and they randomly select 90 students for the study, and they find that 15 of them are left-handed. Is this evidence that the proportion of left-handed students at the school is different from the population proportion? Okay. And as we kind of scan these questions, it talks about a confidence interval, okay? So we're dealing with a confidence interval. And the variable is whether someone is left-handed or not. So that's categorical, meaning we're dealing with proportions. And how many samples do we have? One sample, right? So we just have one sample of 90 students. Okay, so we can kind of look at this, and we got X, we have 15 students, our N is 90, and so that means our P hat, which would be 15 over 90, that's going to be something like 0.16666, I think. 15 over 90, 1/6 or 0.1, yeah. All right, so 17, what is our sample proportion? P hat would be 15 over 90. Number 18 says you want to make a 90% confidence interval for the proportion of left-handed students. What critical value Z star would you use? Okay, so when making a confidence interval for 90%, our Z star is going to be 1.645. Okay, and that's actually given in our formula table as well. It says Z star values 90%, 1.645 right here. Okay, I'll go ahead and I'll copy this this little section right here. Okay, 90%, yeah, 1.645. Okay, so the standard error is P hat times 1 minus P hat over N. So number 19, our standard error is the square root of P hat times 1 minus P hat over N, so N is 90, okay. So what I'm going to do here is I'm going to do square root, parentheses, answer times 1 minus answer button, close parentheses, divided by 90, root 2 over 36, that's 0.0393, okay, 0.0392837, yeah, whatever. We'll just round that off to 0.0393. Okay, number 20, when making a confidence interval, what will be the center of the interval? The center will be P hat, which we've already established is 1/6. Make a 90% confidence interval, so that's P hat plus or minus Z star times our standard error. So just using this as my standard error, I'm going to have basically 1/6. Here, I'll do this. 1/6 plus 1.645 times 0.0393. Okay, and I get 23.13. 0.2313, and on the low end I'll do minus and I get 0.1020. I get 0.1020 to 0.2313. Okay. Okay, and number 22 asks, based on your interval, is this evidence that the proportion at the school is different from the nation? So here, our confidence interval would just be something like, we are 90% confident that, what's our population here? It's our school, right? So the population that the proportion of left-handed students at the school is between 0.1020, and 0.2313, okay? So we're not gonna, it's quite a big range, and that's because we're basing our interval based just on 90 students, okay? So number 22, based on the interval, is this evidence that the proportion at the school is different from the nation? Okay, the national percentage is 14%. Okay, 14% is in the interval. So we do not have evidence that our school's proportion is different from the national percentage. You good? Any questions? Everything's great? All right, let's go over our next set of questions. Okay, we're gonna, says we buy a bag of Starburst and Jolly Rancher candies. The bag of Starburst contained 80 pieces total, and 12 of them are cherry flavored. Jolly Ranchers have 70 pieces, and 14 of them are cherry flavored. Assuming that these are truly random assortments, does this provide evidence that Starburst and Jolly Ranchers have a different proportion of cherry flavored candies? Okay, it's very important statistical stuff going on here. Okay. Cherry is the best flavor, of course. And so here we've got, well, looking at the questions, it's talking about a hypothesis test, okay? So we've got a hypothesis test. We're talking about whether candies are cherry flavored or not. So these are proportions. And we're looking at both Jolly Ranchers and Starburst, so we have two samples. Okay, and so for this, we have to, we're going to do hypothesis test proportions, two samples. We'll take a look here. Okay, and so, well, actually, before we get started, maybe it'll be useful to kind of just list off all of the stuff we have. Okay, so we've got, as far as Starburst goes, that will be sample 1. And so our N is 80, our X is 12, N1, X1, and so our P hat 1 would be 12 over 80. I believe that's 15%. Okay. And then sample 2 will be the Jolly Ranchers. 70 x2, we've got 14, so our P hat 2, 14 over 70, or 20%. Okay. All right, so 23, what are our hypotheses? Our null hypothesis is that the two proportions P1 is equal to P2. The alternative is we want to know, are they different? So we're going to have P1 does not equal P2. Okay. We could also write them as P1 minus P2 is equal to 0, and P1 minus P2 does not equal 0. Okay. It can also be written that way. So 24 is asking, what is the p hat? P hat is our overall proportion, which is x1 plus x2 over n1 plus n2. So we have 12 plus 14 divided by 80 plus 70, or 26 over 150. And what is that? I get 0.1733, something like that. Okay, the test statistic is going to be our z. So first we got to figure out our standard error, which is the square root of p hat times 1 minus p hat. So 0.1733 times 1 minus 0.1733 times 1 over n1 plus 1 over n2, 1 over 80 plus 1 over 70. And when I punch all of this out, I get something crazy. I don't know. 0.1733 times 1 minus 0.1733 times parentheses 1 over 80 plus 1 over 70. 0.061948. That's not our answer. Our answer is the z-score, which is p hat 1 minus p hat 2 over the standard error. So p hat 1 is 0.15 minus p hat 2, which is 0.2, divided by 0.061948, and I get negative 0.81, I believe. Let me just punch that in. 0.15 minus 0.2 divided by the answer I got. Yeah, negative 0.81. So z is equal to negative 0.81. That is my test statistic. Okay, so the p-value, so as far as the p-value goes, it is 2 times the tail area because our alternative has a not equal sign, right? So alternative has a not equal sign. Our p-value equals 2 times the tail area. Okay, so we look up negative 0.81 and we find that the area to the left of negative 0.81 in the z table is 0.2090. So if I look up in the z table negative 0.81, I get 0.2090. Okay, so area to the left of z equal to negative 0.81 is equal to 0.2090. My p-value is 2 times the tail area. P-value is equal to 2 times that, so 0.2090 times 2, and I get 0.4180. So my p-value is basically 42%, something around there, okay? So my p-value, if we ask what is the conclusion we make, our p-value is greater than alpha. So we do not reject the null hypothesis. And we would say we do not have evidence that the proportion of cherry candies is different for Jolly Ranchers and Starburst. Okay. Do you need me to go back? Are we okay?
So with
And so if our z-score was positive 0.81, okay, if our z-score ended up being positive 0.81, we would look that up and we'd get something like 0.791 or something like that, okay? And in that case, if we multiplied that by 2, we would get a number bigger than 1, okay? And so that's got to be a mistake. So we would have to take the area that we find in the table, subtract that from 1, and then multiply it by 2, okay? So the tail area is to the left if it's negative, which means you just take what's in the table. The tail area is to the right if z is positive, which means you take what's in the table and subtract it from 1. Okay, is that all right? Okay, so the next problem, okay, we want to see if caffeinated drinks improve reaction time is what the question is asking here. Okay, and so it says they select volunteers in a blinded experiment, give some of them caffeine and other people just regular non-caffeinated drinks, and then they record reaction time. Group 1, we had 30 people drinking caffeine, and the average reaction time was 580 milliseconds with a standard deviation of 110. And then in the other group, they had no caffeine, and the average reaction time was 640 with a standard deviation of 130, okay? And we want to know, does this mean caffeine improves reaction time? Okay, well, let's take a look here. Do we have, when we're looking at this, it's talking about p-value and t-statistic and hypothesis test. So we're dealing with a hypothesis test. And we're looking at the average reaction time, so we're dealing with means, and we have 2 samples. Okay, so we're going to come to our little formula sheet and just kind of take the hypothesis test means 2 samples. We'll take this little section right here. Hypothesis test means 2 samples. Okay, and it's asking, number 28 is asking, what should the hypotheses be? Okay, so let's think about this for a second. Okay, so we've got group 1. Sample 1 will be the one with caffeine. Okay, and sample 2 is no caffeine. Okay, as far as sample size goes, we have 30, and our average reaction time was 580, and our standard deviation was 110. The sample size of group 2 was 25. Our average reaction time was 640, and our standard deviation there is 130. Okay, so let's look at what our hypotheses should be. Our null hypothesis, that's easy. It's going to be mu1 is equal to mu2. Okay. The alternative says we want to know if caffeine improves reaction time. So how should mu1 compare to mu2? Mu1 is the group with caffeine. If it improves reaction time, what does that mean? It means your reaction time, you got faster at reacting, right? So the reaction time for the caffeine group should be less than the reaction time for the no caffeine group. Okay, because faster reaction times mean, or better reaction times mean you take less time to respond. Okay. So improve doesn't just necessarily mean things get bigger, okay? Okay, what is the observed difference in means? Okay, here it's just asking what's the difference between x bar 1 and x bar 2. So here we would say 580 minus 640. We have a difference of negative 60 milliseconds, okay? That's the difference that we observed. Observed difference right there. What is the resulting t statistic? Okay, so let's figure out our standard error. That's going to be the square root of s1 squared over n1 plus s2 squared over n2. 110 squared over 30 plus 130 squared over 25. I think if I punch this out, I get 32.85. Okay, so my test statistic t is x bar 1 minus x bar 2 divided by the standard error, 580 minus 640 divided by 32.85. I'm getting negative 1.826. I'm going to punch this into the calculator. Okay, 31. We're going to look this up to get our p-value. So how many degrees of freedom will I be using? N minus 1. I use the smaller n, so I'm going to use 25 minus 1. I'm going to have 24 degrees of freedom. Okay, and we're going to look up 1.826. Okay, so because my alternative has a less than sign, you know, our p-value is equal to the tail, left tail area. And then we look at our test statistic and it's negative, and that works out because when you look up a negative t, basically everything becomes left tail probabilities. Okay, so we got 24 degrees of freedom, and I'm looking up 1.826, okay, or negative 1.826. That would go in between these two numbers at 24 degrees of freedom, which means my tail area is between these two values, is between 0.050 and 0.025. Okay, so my p-value is between 0.050 and 0.025. Or in other words, I can say 0.025 is less than our p-value, which is less than 0.050. Okay, that's our p-value there. Is that okay? All right, 32. Performing a one-sided hypothesis test with alpha equal to 0.05, what is the conclusion that we make? So if alpha is equal to 0.05, my p-value, whatever it is, it's less than 0.05. Okay? I don't know exactly what it is, but I do know it's smaller than 0.05. We would reject the null hypothesis, which means we have evidence that caffeine improves reaction time. So I'm going to just write that right here. Reject the null hypothesis. We have evidence that caffeine reduces reaction time. Or I guess improves. Okay. If that's a mistake, if our conclusion is a mistake, what kind of error is that? We chose to reject the null hypothesis. If it was a mistake to reject the null hypothesis, that is a type 1 error. It's kind of all jammed in there, but I hope you can still make sense of it. Everything is good so far? Okay. Again, I think I'm going to just keep powering through, and then we'll probably finish a little bit early. Okay? And here, I'm going through the entire, so the final, it's going to be 50 questions long. I'm going to finish the entire thing, I don't know, in a couple hours. We got started at like 7:30. We'll finish pretty soon. You'll have the full 3 hours to do the final next week. It should not take anybody the full 3 hours, but I mean, if you're here at 10 o'clock, that's fine. But at 10 o'clock, I'm going to kick you out. So.
What if we bring a cherry starburst? Will we get extra time?
I cannot give you extra time for in exchange for candy. I'm sorry, it doesn't work that way. Yeah. Actually, I'm not expecting anybody to try to do this, but in the past, students have tried to give me gifts, and I have to turn all of your gifts away. It's they have the school doesn't like it when teachers accept gifts before grades have been filed. Okay, so if you remember me after grades are filed and you want to give me a present, there's no rule against that. But there's definitely rules against receiving gifts before grades have been filed. Okay, so I don't think I'm not. Again, I was not expecting anyone to give me a present, but just in case. And just for the future also, if you ever consider giving a teacher or professor a gift, just know that they're kind of bound by these rules. All right, next. It says, in a certain city, a study was conducted to see if the police department had a different proportion of minority employees than the fire department, and researchers randomly selected 200 employees from both the police and fire departments and took note of whether the employee was a minority or not. And I said at the police department, they got 200, and then 80 of them were minorities. And at the fire department, they looked at 200 random employees, and 50 were minorities. Okay. So we've got looking at hypothesis test. We're dealing with proportions. Okay. And we've got 2 samples. All right, let's list off the data here. So sample 1 will be the police, and sample 2 will be the fire department. All right, we've got N1 200, X1 80. So our p hat 1 80 over 200.4. At the fire department, 200, X2. We have 50, so our p hat 2, 50 over 200.25. Okay, 34, write the hypotheses. Hypothesis test proportions, 2 samples. Your null hypothesis is always going to be P1 is equal to P2, or it can be written as P1 minus P2 equals 0. Okay. The alternative is we want to know, are they different? So it's going to be P1 is not equal to P2, or again, P1 minus P2 doesn't equal 0. For this hypothesis test, what's the value of p hat? So p hat is the overall proportion. We're going to do 80 plus 50 divided by 200 plus 200. We get 130 over 400, and that's 0.325. That's our overall p hat. 36, we're going to find our test statistic. So first we got to figure out our standard error. So that's p hat 0.325 times 1 minus p hat 1 minus 0.325 times 1 over n1 1 over 200 plus 1 over n2 1 over 200. I'm going to go ahead and just tell you what that comes out to be. That's 0.04684. And so when we calculate our test statistic z, we're going to have p hat 1 minus p hat 2 divided by our standard error. So I got 0.4 minus 0.25 divided by 0.04684, and I get a test statistic of 3.20. Okay. 37. It says, what's the p-value? Okay. The alternative has a not equal sign, so our p-value is equal to 2 times the tail area. In our case, our z is equal to positive 3.2. Okay, so when we look up 3.2 in the z table, we get 0.9993, I believe. Okay, so positive 3.2 is 0.9993. Okay, area to the left of z equal to 3.2 is 0.9993. Okay, because z is positive, our tail area is to the right. Okay, so tail area of positive z is equal to 1 minus that, 0.007, 0007. Okay, so our p-value is equal to 2 times that, or 0.0014. So our p-value is small. P-value is less than alpha. This means we reject the null hypothesis. Okay, and that means we have evidence that the proportion of minority employees is different at the fire and police departments. And this is just made up information. I have no idea what the demographic makeup of the police and fire departments are. Uh, 39, I've run out of space for this. In the context of this problem, what does it mean to commit a type 1 error? Okay, so I'm not sure where I can write this. Okay, so a type 1 error would be the false positive, right? So here, this would mean we come to the conclusion that the proportions are different okay, but in reality the proportions are the same. So, you know, during election season, they love to split out how people are voting based on their demographic characteristics. And so, you know, sometimes they'll say that, like, people who are like this or whatever, you know, women or minorities or whatever, you know, this percentage is voting and whatever, okay? A type 1 error would be, in reality, this demographic characteristic does not make a difference in how someone is voting, but the report that you're looking at thinks it does make a difference. And you know, these are kind of questions that you should always be thinking about in the back of your mind. Generally, the samples that they take are large enough that that the risk of a type 1 error is quite low, but certainly things are possible. Okay. Okay, just a few more questions here, and then we'll be done. All right. Potatoes, it says, are sold at the grocery store in 5-pound bags. You decide to weigh a random selection of 10 different bags, and you find that the average weight of these bags is 5.2 pounds with a standard deviation of 0.3 pounds. Is this evidence that the bags at the grocery stores have a mean weight different from 5 pounds? So we're going to do a confidence interval. Okay, confidence interval, we're dealing with the mean weight, and we've got one sample. Okay, so we've got x bar plus or minus t star times the standard error, and our standard error is s over the square root of n. Okay, and looking at our data, we've got n is equal, we're just looking at 10 bags. Okay, our x bar is 5.2, and our standard deviation is 0.3. Okay, number 40, how many degrees of freedom do we have? That's n minus 1. We've got 9 degrees of freedom. Okay. At the center of the interval, we're going to plug in x bar. So we're going to put in 5.2. And our standard error is s over the square root of n. So we're going to have 0.3 divided by the square root of 10. And I'm getting 0.0949. Okay. Let's just plug this in, make the confidence interval. Okay, so I've got 5.2 plus or minus, we're going to go to 9 degrees of freedom, 95% confidence, t star, I'm getting 2.262. I think we used that number earlier today. T star is 2.262, 95% confidence, 9 degrees of freedom. And we're going to multiply this by our standard error of 0.0949. And when I do this, 5.2 minus 2.262 times 0.0949, 4.985. To, on the other hand, 5.414. Okay, 44, what is our conclusion? Okay, so 5.0 is inside the interval. Okay, so at the 95% confidence level, we do not have evidence that the mean weight of bags is different from 5 pounds. Okay. If we reduced our confidence level maybe to like an 80% or even a 90% confidence interval, we might find that 5 is not in the interval. Okay, and in that case, we would say, you know, at the 80% confidence level, we have evidence that the mean weight of bags is different from 5 pounds. Okay, and it's okay. It's just we're now less confident in our answer. Okay, if you wanted to be extra confident, then you're not going to be so quick to make these judgments, right? If you're on the jury and they say make a decision based on beyond a reasonable doubt, that should give you pause before you go ahead and say guilty, okay? But on the other hand, if you're in a civil case, which rarely goes to jury, but sometimes it does, you know, the level of, I don't even know what the term is, but the level is not beyond a reasonable doubt. It's something else. I forget the phrasing, but it's lower for a civil case than a criminal one. Almost all civil cases are decided in arbitration and a series of depositions these days anyway. Every time you read the final print, it says, not every time, but a lot of times when you sign away these things, they say like binding arbitration, you don't, where they pick the person who's going to be deciding these cases for you. They're moving it away from stuff. Okay. Yeah. Whatever. Okay, last set of questions. It says a fair die should land showing the number 4 1/6 of the time. You roll the die 100 times and count how many times it lands as the number 4, and it lands as the number 4 20 times. Is this evidence that the proportion it lands number 4 is different from 1/6? And here it's talking about hypotheses, so we're dealing with a hypothesis test. We've got proportions, and we have one sample. Okay, so looking at our data, we rolled the die 100 times. It landed on the number 4 20 times. So our p hat is 0.2. The hypothesis for proportions one sample is p is equal to some number p0. So in this case, p would equal 1/6, or you could write p is equal to 0.1666 whatever. Okay, and then the alternative is that it's different. So our alternative here would be that p does not equal 1/6. The sample proportion p hat is 0.2, 20 out of 100. Okay, what is the standard deviation of your sampling distribution? What is this another term for? Standard error, right? So our SE is the square root of P0 times 1 minus P0 over N, okay? Again, given in the formulas, P0 times 1 minus P0 over N. So I'm going to just do 1/6 times 1 minus 1/6, or 5/6 divided by 100. And when I do that, I'm getting 0.03727. Okay, our test statistic Z would be p hat minus p0 divided by the standard error. So I get 0.2 minus 0.166667 divided by 0.03727, and I get 0.89 as my z-score, rounded off to 2 decimal places. Okay. So that's my z-score. 49. To make a conclusion, we got to figure out our p-value, right? So our p-value, because so the alternative has a not equal sign, so p-value is equal to 2 times the tail area. So when I look up 0.89, our p-value is going to be 2 times 1 minus, when I look up 0.89 in the z-table, I get 0.8133. So So I get 2 times 0.1867, which equals 0.3734. So that's our p-value. Okay. So our p-value is equal to 0.3734, which is greater than 0.05. So we do not reject the null hypothesis. And we would say we do not have evidence that the die lands on 4 different from 1/6 of the time. In reality, nobody really, like, you might think in Las Vegas they want to make sure that the dice rolls fairly or something. They rarely test these out. They just replace the dice. It's much cheaper. Rather than trying to test out the dice, they just, you know, there's a few high quality dice manufacturers and that have strict tolerances. And you know, after several hours of playing craps or something, they just throw those dice away and bring in new ones. Things like that. It's much cheaper that way. Okay. And in fact, if you but you go to the, you know, Target and you buy dice, those dice are not even close to being those don't have strict tolerances. And like, so if you stack them all with you know, like the number 1 facing you, the stack might be like this tall. If you take like 10 of them and you stack them up this high with the number 1 facing you, they might be this tall. And then if you stack up 10 of them with the numbers, you know, 4 facing you, it might be like a little bit taller, a little bit shorter, things like that. And you can like try testing out on your own, but it's like, you know, if you get 20 versus 100, it's not a big deal. So it's hard to test these things out in real life without doing like close to you know, several thousand of these. Okay, let's look at these ones here. Okay, sampling methods. Okay, it says Major League Baseball wishes to conduct a survey of its players. Instead of trying to create a list of all players from all of their teams, they decide to randomly select 4 out of the 30 teams, and then they're going to survey all of the players on those 4 selected teams. Okay, what kind of sampling is that? Yeah, cluster sampling, right? So the teams here act as clusters. Oh, what's going on? So this is cluster sampling. Okay, they want to survey its employees. They take a master list of everyone in the company and randomly selects 100 of them for the survey. What kind of sampling is that? Simple random, SRS. Okay, they're going to go to a bridge. They talk to, instead of talking to all of the drivers, they decide to stop every 10th car that passes through. Systematic. Okay, easy. All right, and then a few miscellaneous questions. Of course, none of these questions will be on the final, but these are kind of the idea that we're going for. Okay, so what do we have? A bar chart is used for what kind of data? Bar chart. Categorical, right? And what do we have for numeric data? Histograms, dot plots, box plots. Okay. All right, in a normal model, approximately what proportion of data are within 2 standard deviations of the mean? About 95%. That's the empirical rule, right? The intercept in linear regression would be our predicted value when x has what value? when x is 0, right? What's the slope? What's the definition of the slope? It's how much we expect y to go up every time we increase x by 1. So if we bump up x by 1, we expect y to go up by the slope. Okay, if the probability of A and B happening together is 0, that means A and B are mutually exclusive, right? What does it mean to be independent? The independent means that the outcome of one has no influence on the outcome of the other. So the probability of A happening, if B has already happened, is just the probability of A happening, whether B has happened or not, okay? For quantitative is another word for numeric variable. For a numeric variable, if there's only one peak in the histogram, how do we describe the shape? That would be unimodal, right? What does it mean to be skewed? You're skewed, okay, so if it's skewed left, what does that mean? That means you've got most of your data up in the high area, and you've got some outliers on the lower side, right? Okay, right skewed would be the opposite. You've got some outliers on the high side. Which measure of center is not heavily influenced by extreme outliers?
Median.
The median, right? Whereas the mean is. Conceptual definition for the median?
Middle number.
Halfway point. Conceptual definition for the mean? The balance point, yeah. So you can expect, so the stuff from chapters 1 through 6, you know, it'll be kind of more like this, conceptual and definition and based, not no calculations. So, okay, good luck, you guys. We'll see you in a week. It's been a pleasure. Good luck as you guys study.